for finding 3 by 3 determinants, there's a special method that works in this case. And here's how you do it. What you do is you take the matrix here, and to find its determinant, you copy the first two columns again. So A, D, G, B, E, H, and then you multiply. What you do is you multiply along the diagonals. So you get this, this, and this. So those are going to give us AEI plus BFG plus CDH. And then for the back diagonals, we do those as well. But those we subtract. It's kind of like in the 2 by 2 where you do AB or AD minus BC. The backward diagonals you subtract. And same thing here. So this would be minus CEG minus AFH minus BDI. And so this little system, this works for 3 by 3s. Now, warning, this does not generalize for 4 by 4 and bigger. So don't use this on a 4 by 4 or 5 by 5 or anything like that. The thing that makes it really insidious is sometimes doing it with the 4 by 4 will work and give you the right answer, but it doesn't work all the time. So don't try using this method on a 4 by 4 or larger. If you do, you're not guaranteed to get the right answer, and I won't give you credit for it. All right, so let's see. Why do I have 3 examples here? Well, let's do them. All right, this first one, 4, 3, 1. I'm going to copy that. Then 1, negative 1, 9. And so my determinant here is going to be 4 times negative 1 times 5. Let's see, I'm going to go ahead and multiply this out. So that's going to be negative 20. The next row is 0, or the next diagonal is 0. And then 2 times 3 times 9, that's 6 times 9 is 54. And I'm going to subtract the others. So I'll do these in orange. When I subtract these out, I get, let's see, minus negative 2, minus 0, then minus 15. So whatever that is, I'm going to be lazy and do that with my calculator. Let's see, negative 20 plus 54 plus 2 minus 15. That gives me a determinant of 21. All right, let's look at this next one. 4, 4, 1, 2, 2, negative 5, 1, 1. Oh wait, I don't need that last one. So this one, multiply that out. Let's see, we get 8. 2 times 1 times 1. Then 1 times 4 times negative 5. Then we'll subtract the other diagonals. So we'll subtract 2. We'll subtract negative, what is that, 20? And then we'll subtract 8. Interesting. So let's see, I could do this one without my calculator. That looks like it winds up giving us 0. Oh, this does give us 0, yeah. It gives us 0, and if you look back in the original matrix, notice, I should have been paying closer attention. Those 2 rows are exactly the same. Anytime that happens in a determinant, in a matrix, the determinant is going to be 0. And it would be the same if it were 2 columns that were the same instead of 2 rows. Anytime you got a repeated row or a repeated column, determinant's going to be 0. Let's work this one out now. Copy this 1, negative 2, negative 1, negative 5, 2, negative 3, and I want to do the 3 forward diagonals. Let's see, we get 14, we get positive 20, and then we get plus 18. right? When we do the reverse diagonals, or backward diagonal, what do we get? Let's see, we're subtracting off -6. Then we're subtracting off -12. Then we're subtracting off +70. So when I do that, I get 14 plus 20 plus 18 minus, or no, it's actually plus 6 plus 12 minus 70. And that gives me 0. Okay, so this one gave me 0, and if you look back at the original thing, I'm gonna erase all the highlighting. Let's see, do we have one row or one column that's a multiple of the other, or is exactly the same? If you look at it, the answer is no, but somewhere in there is a linear combination. Now, this is not necessarily an easy thing to find, but let's see, if we do the top row minus, or no, if we add these two rows together, I think that'll give us the third row. 1 minus 2 is -1. -5 plus 2 is -3, and 3 plus 4 is 7. So there is a linear combination among there. And those things are not always easy to spot. This leads us to a handful of facts. If any of the following things are true, then the determinant is going to be 0. If 2 of the columns are the same, or 2 rows are the same, then your determinant is 0. If one row or column is a linear combination of the others, then your determinant is 0. And we didn't see one of these, but this one I think makes good sense. If a row or a column consists of all zeros, your determinant